love it so much. It's like how you need like prerequisites.
Someone who's trying to pull up price top.
Yeah, I get it. It's like, oh my god. People are like, what? I don't get it.
I have housing inspections on my list. No, I want to get the lecture started. You have to come back sometime. I can't go through all the tests in house. So, what time will be appropriate? I'll mail you. Email me. Yep, email me. Yep. We have life. Sort of. In the break, I'll hand back your tests and I'll show you a bit about the marks everyone got. But for now, we're going to do logic. We're not going to use the stupid computer because the stupid computer is being stupid. Okay. Logic is really important. Some knowledge of logic would have helped you with some of your set stuff and will in the future help you with sets as well as other things, as well as just logical arguments, clear thinking, programming, for those of you who are doing programming, all sorts of things like that. Now, with logic, this sort of logic, we're dealing things which have two answers, either yes or no, true or false, which we can assign 1 or 0. So we're looking at things where there are precisely two options. And of course you can combine these to give yourself quite a few options. Like the logic and the Boolean expressions we're looking at deal with two options, and from there you can do wonderful things. So, oh, amazing, we have a live computer. Here's an example. I wear a jacket if it's cold or if I'm going outside on a rainy day. So the decision whether to not to wear a jacket is based on the answer to three questions. And each of these three questions is a yes-no question. We need to know, is it cold? Am I going outside? Is it raining? Now we're going to encode our answers as 1 for yes, 0 for no. And what I'd like is, let's imagine we're going to get a robot to as a butler, and so the robot is going to know whether it's going to hand me my jacket or not. And we want a function that we can program the robot with so that once it knows the answers to those three questions, it knows whether to hand me a jacket or not. So, let's say the answers to questions 1, 2, and 3, that's is it cold? Am I going outside? Is it raining? Let's call the answers X, Y, and Z. So that's The answer to that one is X, the answer to that one is Y, and the answer to that one is Z, and it'll be 1 if it's yes and 0 if it's no. So there are 8 possible things that can happen, 8 possible scenarios. It can be yes to all the 3 questions. It can be yes, yes, no. It can be yes, no, yes. You know, there's 3 questions. For each, there's 2 possibilities. So there's 2 times 2 times 2, which is 8 different scenarios we can have here. And they're all listed there in a table. The answers to the first question, the answers to the second question, the answers to the third question, and all possibilities are there, aren't they? Yes, they are. Right. Now, our function tells us whether I'm going to need the jacket or not. And we better go back and look at it. I wear a jacket if it's cold or if I'm going outside on a rainy day. So if it's cold, I'm going to wear a jacket. I don't even need to look at those. I know it's a 1 there. I'm going to wear a jacket. Or if I'm going outside on a rainy day, meaning it's a yes and a yes for those 2. So I put a 1 there. And that's, in those 3 cases there, I don't wear a jacket. So that table describes the function. Agree? Right. Now, we've got a function we can use. This can be automated. It can also be used to make things really clear about what the instructions are, even if I've got a human butler. So let's talk a little bit about the functions and the setup we have here. We have a set of just 2 things, 0 and 1, yes and no, which we're writing as 0 and 1, no and yes. So let S be that set. And for our function, we had 3 inputs, or at least you can think of it as 3 inputs, the answers to the 3 questions. But each set of answers forms a triple of symbols. Yes, 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 no. They're the 8 possibilities. Look, there's all 8 there. The 8 possible scenarios, the 8 possible inputs. Now, each ordered triple is an element of this set. So drag your brains back a month where we did sets and we looked at the Cartesian product of sets. The Cartesian product of 3 sets just means ordered triples, where each element, that element's from that set, that element's from that set, and that element's from that set. That's not difficult, it's just a triple, where the first element's from that set, etc. And S, Cartesian product S, Cartesian product S, funnily enough, is abbreviated as S cubed. It's not normal multiplication, but we still abbreviate it as S cubed. And you know S is a set, so you understand the context. Now, these are the set of inputs for the function. That is, this set is the codomain, the 8 possible things you can put into the function. The output is a 1 or a 0. A yes, you wear your jacket. A no, you don't. So the codomain is S, just S, a 0 or 1. So we have a function. So that's just an example of a Boolean function. Now, Boolean stuff, it might be a new word to you. For how many of you is the word Boolean a new word? A few of you, maybe? I can't believe you all know a lot about Boolean. Unless some of you, you've mentioned it in programming for some of you, but you're not all doing programming, I know. All right, so some of you have heard it before. Named after George Boole, I think. Somebody Boole, anyway. Boolean stuff is on the whole easy. I think that's one thing to remember. Boolean stuff is on the whole easy. We'll see. There's nothing particularly tricky in this lecture. Not as tricky as proofs. Not as tricky as some of the counting problems. Oops, I'm not wearing my thing. I'm in trouble. So this stuff is actually quite friendly as well as incredibly useful. So a Boolean function is a function which takes as inputs ordered maybe pairs, triples, or maybe ordered 5 tuples or 6 tuples or whatever, and it does something and gives you out a 1 or a 0. Quite a simple thing, really. It's a function. So our jacket function was a Boolean function, and here are a couple of other functions. With these, the inputs are just from S cross S, which means an ordered pair where the first element is a 0 or a 1 and the second element is a 0 or a 1. And in that case, there's only 4 possibilities. The domain consists of 4 things, and there's the outputs listed there. They're different Boolean functions. Okay. Now, we write x, y there because if that's x and that's y, then the inputs to the function are x and y in that order. What you're used to is just a single input in maths, but you can have 2 inputs or 3 or 564 or infinitely many. Okay. Now, how many Boolean functions from s squared to s are there? That's functions of this sort. S squared is s cross s, so there's only 4 possible inputs. The domain has only 4 elements. How many Boolean functions are there? G and H aren't all of them. I could write out a few more. How many are there? There's clearly 2 at least, because there's 2 there. 16. Who said 16? Okay, I've still got some Easter eggs left. Which I would like help with. Thank you. That's 16. Because if I'm going to choose a Boolean function, I start with that. I've got 2 choices for what to put there for the image of 1, 1. 2 choices for what goes there, 2 choices for what goes there, 2 choices for what goes there. So it's 2 to the 4th, which is 16. Yes. Okay, how many Boolean functions are there from s cubed to s? What do you think up the back? Let's go back to our jacket function. Where did I put my jacket function? Ah, right. This is an example of a function from s cubed. So that's just one function. There's lots of different functions I could have here. How many are there? Actually, I wrote down the wrong thing. I wrote down the wrong thing here. I'm leading you astray. 2 times 2 times. No, that's right. Okay, sorry. 2 to the. Yep. Let's write it down here. How many choices do we have for what goes there?
2.
And how many choices do we have for what goes there? 2. And I think we get the pattern. How many here?
2.
How many 2s do I have down here?
8.
Yep, that's 8. 2 times 2 times 2 times 2, it's 2 to the 8. So that's one of the answers that was given, 2 to the 8. Yes. You all realised it was a power of 2, and 2 to the 8 is correct. What about S4? 2 to the 16. Okay, what does everybody else think? Okay, you're all under the 2 to 16. You've got a lot of friends there. They all agree with you. It's clearly very persuasive. Not to mention correct. If I had 4 inputs, my table would be twice as big. I'd have 16 rows and 16 choices down here instead of the 8 we had. So it's 2 to the 16. What about there?
2 to the power of 2n.
Oh, I love this. 2 to the n, 2 to the 2n, 2 to the 2 to the n. Any other, does anyone want to say 5 or something like that?
2 to the, I want to say n minus 1. No, hang on. 2 to the.
Firstly, have a look and see what the pattern is for 2, 3 and 4. See what the pattern is when n is 2, n is 3, n is 4.
It's 2 to the power of the size of the power cell. So 2 to the 2 to the n would be correct.
Okay, there's an argument and a vote for 2 to the 2 to the n. Does 2 to the 2 to the n at least fit the pattern we've seen so far? Because that's 2 to the 2 squared. Now, when we write a to the power of b to the c, it's as though there are brackets there. Okay? That's so if to keep you happy if you want, so that there's no doubt about what we mean here, I'll put brackets in there. And that fits what we've got. 2 to the 2 squared, 2 to the 2 cubed, 2 to the 2 to the 4th, 2 to the 2 to the n. So that's correct. And if you think about the tables, it was 2 to the power of the number of rows in the table. So how many rows if you've got n things here? How many rows if you've got n things? Well, if you've got n things here, then you've got 2 possibilities there, 2 possibilities there, 2 possibilities there, 2 possibilities there. So it's 2 to the n rows, and then it's 2 to the number of rows, which is 2 to the n. So it's 2 to the number of rows in table. That's maybe a way of thinking about it. Can you actually read that? 2 to the number of rows in the table. Anyway, you will be dealing mostly with tables with or things with 1 variable, 2 variables, 3 variables, and if you do get stuck with 4 variables, you'll be working with things that are small enough for you to write them all out. And when you're good at that, you'll then start to be, the generalisation will be easier. Now, it's a little bit like a technique I saw some of you do in the class test for one of the counting problems. There are a lot of mistakes in counting problems, but some of you took the approach of, clearly, I'm not sure, so I will write them all out. And so some of you got the correct answer to the question on, it was the same answer, turned out on this case it was the same answer for each test. The answer was 21, not 20 numbers which were divisible by 5, I think. It was 21. And some of you got that by writing them all out. Now, there's nothing wrong with that. If you're not sure and you can do it, then yeah, do it the hard way. If you can't do it the easy way, but you can do it the hard way, then do it. And that won't help you so much with the next test, which will be find the number of numbers divisible by 7 between 1 and 536, 4 million. It won't help you with that, but in a sense it will. Because if you're not sure about how to do something and it is too big to write out, you can do a small one and write it all out, another small one and write it all out, make sure you know what's happening, get a feel for it, and then generalise to the big one. So, in this case, even if you can't remember, you can always write out your tables, see how many rows, and think about this. Okay, I get distracted because where were we? Oh yes, we were Boolean functions. Boolean functions, lovely things. Well, we're probably not going to bother with anything because in that case, you've got a function. You've got a function from the empty set to and your codomain is 0, 1. And then how many functions are there from the empty set to that set?
None.
It's going to be none or 1, isn't it? It's the empty function. There is 1. 1 function. This is one of these tricky, think about 0 ones.
Does that align with our rule of 2 to the 2 to the n?
That is what we're just going to check, and that is a really good question. That's the question we should ask. Okay, so 2 to the 2 to the n, 2 to the 2 to the 0 equals 2 to the 0 is, oh, it doesn't, does it? But if we've got a table This is interesting. If we've got a table, there's nothing in it. And so it's 2 to the 0 is 2 to the number of rows. That works out, which is one function. But it doesn't align with that, does it? Isn't that interesting? 0 can be a pain sometimes. I think that's the lesson there. 0 can sometimes be a pain. Okay. And maybe that's worth thinking about. Maybe if we think about it another way, there'll be a way of making it fit. But I don't think so. Not in that case. Interesting. Okay, you've given me something to think about for this afternoon. And I'll give you something to think about. Now, this is just a bit of fun. I'm not going to talk about this. This is just a light interlude from James, who wants to annoy you. I can't read it fast. Half a minute.
This one.
All right, thank you. Yes?
Turn the lights on, then turn them off, and then go up and feel the heat in the bulb.
Okay.
That works, but only if you turn on 2 of them,
Turn on
and
one
then
of them,
turn
wait
one
for the
off, and then walk up. And then one's cold, one's warm, and one's on. That's what I was trying to say.
Right. Okay. Yes, you've essentially got a solution there. So, and this is that's a bit of a trick. So I actually don't like this puzzle all that much, but there are some other logic puzzles I love. But anyway, that's James having a bit of fun with you. So we'll leave that, and if you want to talk to me about this later, you can. But it's essentially exactly what was said. If you have one on for a while and turn it off, when you go up, it'll be warm. And that gives you enough information with the other stuff to distinguish the 3 bulbs. Okay. Now, let's get on to something more useful. Imagine we have 3 switches controlling a circuit. And we'll call the switches X, Y, Z. Now, an electricity flows through a gate, or a gate is a switch, if the corresponding switch is on. So I just think of these as one thing. So if it's on, current flows, arrows show, so the current will flow along there if it can. If something's off, it can't flow through. Okay. Which combinations of X, Y, and Z being on and off represented as 1, 0, so 1 is on, 0 is off, will result in the flow of electricity from left to right. Now, this can be represented by a Boolean function as well. We've got 3 variables, which can be 1 or 0, and what we want to know is, does current flow or not? So again, we've got something that can be represented by a Boolean function. And our function will be 1 if the combination of switches gives us electricity flowing, if the whole thing works, 0 otherwise. So there's how...
Is Y and Z dependent on each other? So if the Z's off but Y is on, the electricity will flow?
No, these are independent of each. It's just 2 separate switches. So, but to get current to flow, you'd have to have Y being on and Z being on. You'd have to have them both on. So if one of them is off, even if Z is on and Y is on, you can't get current flowing. Okay, so here's our picture, and we've got a table here which describes what happens. So if X is on, doesn't matter what's here, the current can flow via that way. If you don't like the idea of current, think of water. You'll get flow there. So as long as X is 1, we're going to get current flowing. It doesn't matter what the others are. Okay, now for the other cases here, the only way we can get, if that's off, the only way we can get current flowing is if it goes this way, and the only way that can happen is if Y is on and Z is on. So y is on and z is on gives us 1 there. And the other cases give us 0. So that's the Boolean function that describes that circuit. And you've seen this before. That's our jacket example. It's exactly the same table, exactly the same function. So this circuit tells us how we could wire up our robotic butler. Okay, so we can have circuits represented by Boolean functions, and we can play with these. Okay, so that's this just says what we saw, but there's some symbols we use here. So electricity flows exactly when, if and only if means exactly when X is on, or Y and Z are both on, or both. So this or here means this or both. Current flows if that's on, or these are on, or both. So this or means one or the other or both. That's a long way of saying or, but I think I talked about this some weeks ago. There's two meanings of the word or in the English language. There's one where you can have this or that or the other, and there's one where you can have this or you can have that. X or or. Yeah, yes. So we do have different symbols for them in programming, in logic. So this is what's called inclusive OR because it includes the case that you can have both. This is where you go into a buffet and you can eat as much as you like. For dessert, you can have cheesecake or you can have pavlova, or you can have both because it's a help serve yourself buffet and you can take as much as you like. However, if you pay an expensive restaurant and pay $20 for one dessert and then they wheel out the trolley and say, here, you can have cheesecake or you can have pavlova, but you've paid for one dessert. You get one or the other, but not both. That's exclusive OR, where you can have one or the other, but not both. See the difference? Okay, this is one or the other or both here. This is the OR where you can have your pavlova and your cheesecake. You can have them both. Okay, so we abbreviate to this to X because we've got X is on, or, and that's that same or, we've got Y and Z. So that is abbreviated to that. X means we've got X is on, or both Y and Z are on. Now we've got symbols for or and a symbol for and, as you can see here. Now, you're just going to have to remember these symbols. I'll say a little bit more about them later. That's or and that's and. Remember them. Now, when we say sometimes the and is suppressed, that sounds a bit funny, doesn't it? But it's exactly like, say I have 2 plus, no, say I've got X plus Y. No, I won't use X and Y's because they're logic symbols here. I'll do A plus B times C. There's an algebraic expression that's not unlike what we've got here. I don't need the brackets because we know that multiplication has precedence over addition, so we do the multiplication first. But we often suppress the times. We write that as A plus BC. So that's what it means by suppressed. And you don't have problems reading that. You know that that means B times C, don't you? You've known that since you were somewhere in high school. Okay, so that's the idea here. Sometimes this will be written as this, which means we just leave out the and, or even that. So when we leave that out, it's assumed that there are brackets there. There's quite a few conventions here. And with a little practice, you'll get used to them. They're not hard. Okay. Let's look at this circuit here. we have 3 switches. So what happens with this Boolean circuit can be described by a Boolean function with 3 inputs. We'll do this with a table because this is the easy way to do it. Just write out all possible inputs. Now this is the sort of thing that makes Boolean functions easier than other functions. Because if you do a function like f of x equals 3x plus 5, the sort of function you saw in your test, or sine x, which you've used maybe in school, those functions have infinitely many possible inputs. So you've got to deal with them in some general way. But Boolean functions have a finite number of inputs and you can write them all out. And that means that actually makes them easy in many circumstances. But you don't have to write them all out. And that gives you an option too. Boolean functions are great. Okay, let's check the first few rows at least to see that this table captures what's going on in this circuit. First line. When X, Y, and Z are all on, does current flow through the circuit? Yes, it can go this way and it can go this way. So that's a 1. That's right. So current flows. All right, the next row, when X and Y are on and Z is off, does current flow? No, because if Z is off, you can get to that far and then nothing happens. So the 0 is correct there. So you can check all the way through. That table describes that Boolean function. That table gives you everything about the Boolean function. Now, here are some tables of Boolean functions. Now, one of these, this is the one we saw. This is the one we saw back here. That was this one with this, with this circuit here. And it's XOR brackets Y and Z. XOR brackets Y and Z. Now, when you're writing these out with the symbols here, always use brackets. Always use brackets. Otherwise, there's ambiguity about what you're doing. Okay. Unless you know there's a very good reason not to use brackets, and there are some cases where you don't have to, but if in doubt, use brackets. Okay. Now, we've got a function here. That actually aligns with this one here, with this circuit. Oh, and I didn't say that circuit. That's X or Y and Z. We actually didn't check that. We should have checked that. Does that describe here? It does, because we've got to have Z on. If current's to flow, we must have Z. So we've got to have Z and either X or Y to get current to flow. Do you agree? Right. So it's X or Y, one of those, and Z. So that describes that function. So that's what's been written here. These are the 2 Boolean functions you've seen so far with 8 inputs. And they look quite similar, don't they? It's only the brackets that are different. They're both X or Y and Z, X or Y and Z, but the brackets are in a different place. But look, the functions are different. That's why you've got to have brackets. Because if something mixing an and or an or, and you move the brackets, you change the function. And that's what this shows. Because look, with this input, you get different outputs depending on where the brackets are. Now, you know that, so this is not a surprise, because 2 times 3 plus 4 is probably different to 2 times 3 plus 4 if I put the brackets in a different place, because that's 24 and that's 10. Yeah, you're familiar with that sort of thing, aren't you? Okay. So we see that these 2 expressions here are not equal. And, well, I've said all that. Lesson here. Brackets are important. Got that? Good. Now, let's go back to some basics. what are the basic things we're going to deal with Boolean expressions? We're looking into what's called Boolean algebra, where it's not your ordinary algebra from school, where we've got numbers and we have plus, minus, times, divide. That's school algebra, which you still need to know. We're looking at now Boolean algebra, where we have Boolean expressions, Boolean things, zeros and ones, and we're not going to add and subtract and multiply and divide. We're going to use, the operations are and, or, and there's another one we'll be using, which is not. There are other operations that one can use, but we're just going to use and, or, which is inclusive or, and not. So here they are. The or, that's the x or y or both, the or. We can represent this by this circuit. And over, this means that we get something happening if we've got x or we've got y on or both. Now I'll just flip over to the next slide for a moment because that's captured here in this table, where if we've got x, both x and y on, x or y is 1, current flows. If we've got one of them on and the other off, we still get current flowing. But if we've got neither of them, then no, nothing happens. That's or. Okay, and that's represented by that circuit. So that's one of the three symbols, one of the three operations, Boolean operations. Here's the other one, and, x and y. You've got to have both for things to happen. X, y. You're not going to get anything current flowing unless you've got x and y both on. So the only way you'll get current flowing is to have x on and y on. And that's captured in the table over here with the and. That's our and. The only way you'll get current flowing is if you've got both x and y. The only way you get a 1 is to have x and y. That's why that's called and. X and y. You only have x and y when you've got both of them. You don't have it here because you don't have both x and y. Here, you have a 1 when you have x or you have y. You have both of them here, so it's a 1. You have x here, it's a 1. You have y here, it's a 1. As long as you've got x or y, you've got a 1 here. Okay, and our last one, not. Not changes things. So you could think of not as a switch that's incorrectly labelled. I don't care how you think of it, but what it does is that it's not x, it's called not x, and for electricity to pass, the switch must be turned off. So you could think of that as a switch that's incorrectly labelled. But not is extremely useful in logic. And here is how you describe it. There's only a single input for x, which can be 1 or 0, and the output is the opposite. Not 1 is 0, not 0 is 1. Not yes is no, not no is yes. So you've got 3 simple operations, and these are all really easy. Bit of practice, get used to the symbol, and anything we do with these is going to be easy. There's nothing really difficult about this stuff. We can, of course, get more complicated expressions, but we can build them up very, very slowly, literally bit by bit, and this isn't hard to do. So say I want to get, for example, to x or y in brackets and then not, so that's not all of x or y. Well, rather than do it in one go, it's always a good idea to do things step by step, as some of you did not do in your test and therefore lost marks. I want to rub that in because I don't want to see you stuff around and lose marks in your next test. Step by step is good. Okay, x or y means it's going to be 1 if we've got x or y, or both have being 1. So x or y is not too hard to do, especially when you're doing it for the 10th time, then it gets dead easy. Now, we're taking the whole of x or y and we're looking at not that. And what not does is, here's my previous slide. Not changes 1 to a 0 and 0 to a 1. It reverses it. It negates it. Okay, so 1 goes to 0, 1 goes to 0, 1 goes to 0, 0 goes to 1. That's easy, isn't it? It is easy. Okay, now, let's now work out, let's go for the blue one, x dash or y dash. Well, step by step, bit by bit, if x is 1, x dash is 0. X is 1, x dash is 0. X is 0, x dash is 1, x is 0, x dash is 1. You won't make a mistake doing that. And neither will you make a mistake calculating y dash. If y is 1, 0, 1, 0, y dash is 0, 1, 0, 1. You change every 0 to a 1, every 1 to a 0. You change every bit. Then x dash or y dash is that or that. Now it's going to be 1 if we've got x or y being 1 or both being 1. So we get 1s there and 0 there. Oh, look, this tells us something. Compare that and compare that. They're the same except for brackets, aren't they? But they're different functions. Once again, brackets are important. Okay, here's another function, x dash and y dash. Because we've already calculated x dash and y dash, we can calculate x dash and y dash really easily. 0 and 0s, no. That and that, nah. No. 1 and 1 is 1. To get 1 here with and, you've got to have 1 here and 1 there. And then that gives you 1 here. Ooh, something interesting. Look, those two are the same. Well, that's interesting, isn't it? This expression is the same as that one for every possible input. That means as logical expressions, as Boolean expressions, they are equal. Okay, so we found out two things. Let's summarise that here. These two, once you put the brackets in, it changed it. So putting the brackets in changed it. But then when you look at these two here, they're equal. They are equal because for every possible input, you get the same output. They're equal. So that tells you that x or y and then negate the lot is equal to x negated or not x and not y. Okay. Now, compare to sets. Remember sets? De Morgan's laws? You might have forgotten, but this is one of them written here. If you now have two sets, if you've got some sets, and if you write, so imagine here, let's just draw a picture of the sort of thing I want you to think about here. U is because we've got some universe in which we're working or some context, and in here we've got x or y. That's the sort of picture I'd like to think about for this example of two sets. We've got two sets, x and y, and we can take their union and their intersection, and we can take the complement of those sets in U if we want. Now, let's write x dash as the complement of x in U. Now, this is not just for now. X dash is used in some textbooks as the complement of x in U. It's a notation that is used. Unfortunately, there's several different notations, symbols that are used for the complement of one set in a universal set. And that's a bit annoying. You might pick up another book and find there's a different notation. But it's happened because logic is so useful in so many different areas that it's grown up in different areas with different notation. And that's something that is a pain and we have to deal with it. It's like for quite a few of you program, you change languages from C to Java to something else, and you'll find some of the symbols change, some of the logic symbols change. I think the exclamation mark is not in Java. I can't remember what it is in C, But I know if you're looking at a different language, some of the basic symbols change. You've got logic symbols in your language. You've got symbols for other things, string concatenation and various other things which I can't remember now. But they're different in different languages. And maybe there are good reasons for that, and sometimes I'm sure there aren't. But it's something that you've got to cope with. You've got to cope with that everywhere, actually. Okay. Anyway, that, when you rewrite De Morgan's law for sets, it looks a lot like that, doesn't it? You've got your union here, you've got your OR, and you've got the same sort of thing. If you remove your brackets, you put your dashes there and turn your symbol upside down. If you remove your brackets, you put your dashes there and you turn your symbol upside down. Now, this is more than just a nice example. And I don't know whether we end up doing a lot of this, but union for sets is very much like AND in logic. Intersection for sets is, OR. Union is very much like OR. Intersection like and the complement is like the not. And if you write out all the identities we have with sets using those, you will get identities for logic which are correct. And the reason for that is, to say something is in X union Y means that it is in X or it is in Y. So the definition of union uses or. The definition of intersection, something's in the intersection of X and Y if it is in X and in Y. It's because the definition of intersection uses and. And the complement of X in some universal set U, some big set if everything's in there, is the set of elements that are not in X, not in X. Each of these is defined in terms of the corresponding logical symbol. So there is a really strong connection between the logic and the sets. It means you can use your logic to work with sets. Okay. A Boolean expression is something we construct with these. We might have variables like X, Y, and Z. You can use other letters. Zeros and ones, which we think of as yes or no, or we often think of true or false. 0 for false, 1 is true. Some people like to think of our Boolean expressions, always think of them in terms of 1 is yes and 0 is no. Some people always think of it as 1 is on and 0 is off. I usually think of them as 1 is true and 0 is false. In some sense, they're slightly different contexts and all of them are valid. Okay, so we've got our symbols 0 and 1, which represent true or false, or yes, no, or on, off, if you're working with circuits. And then we have our operators or connectives. With algebra, we've got plus, minus, multiplication, divides, etc. But with Boolean expressions in Boolean algebra, we have and, or, and not. And we can combine them to make really fun and interesting expressions. Okay, now, just like multiplication, and is sometimes suppressed, so x and y will, in some contexts, often be written as just xy. Just like for algebra, a times b is often written as ab for ordinary algebra. It's a handy shorthand. Okay, so there are some examples down the bottom of Boolean expressions. Where we just have a not there, it's like having brackets there. We take not x and then we do the and. All right. We don't have brackets there, and once we get more complicated things, you'll notice that there are brackets here. And where we've suppressed the and, it's a bit like this. It's like this has got brackets around it. We assume they're there. You can write them if you want. So I've shown you some conventions here, but if in doubt, use brackets. Okay, and you can get all sorts of fun expressions. And if you've got quite a few variables, you can get a complicated expression to represent pretty much anything you want. You might want to do more than just drive a robotic butler to tell you when to give you a jacket or not. You can operate complicated anything with expressions like this. You can capture all sorts of things in Boolean expressions. And they're not hard to work with. Okay, a Boolean expression represents a Boolean function. So you can write things out with x's, y's, or's, ands, nots, or you can do the whole table. But it's nice to be able to go between the two. Okay. Let's have a look at an example of a Boolean expression. Note that we've got two variables here, x and y. We're using the connective not and the connective or. This does represent a function. Let's see what the function is in terms of its table. Well, whenever you're writing out a table for a function or for a Boolean expression, start by making sure you've got the right number of rows below the headings. If you've got two variables, you've got two choices for this, two choices for this, so 2 times 2 is 4 different possibilities overall, so you will have 4 rows. Okay, we have 4 rows here. And make sure that you write them out systematically so you cover the 4 different scenarios. That's not too hard. People don't usually stuff that up. That's good. And then step by step, you work your way towards your function. So for this, we're going to need y dash. So we have a column y dash, and from the column y, we calculate y dash. That's really easy. It means not y. Whatever y is, it's not. Not true is false, not false is true, if you're thinking in terms of true and false. And now we'll need x, y dash. Now remember that's x and y dash, which means if we're doing x and y dash, do we have x and y dash? No, we've only got one there, so it's 0. X and y dash, yes, they're both 1, so we get a 1, and so on. We fill in that column, we fill in that column, and finally we come to this, which is that or that. So we do the or there, and we come up with our final column. Step by step, it's really easy. If you do it all in one go, you are sure to stuff it up. And if you do it in one go in a test and you stuff it up, you will probably get no marks. Because I'm in a bad temper when I'm marking tests. I can be really nasty, as you'll see when you get your tests back. Okay, so I want you to get things right and be careful, step by step. And the other thing is, if you make a mistake halfway through, you get half your marks if you do it step by step. And I saw lots of examples of that in marking your class tests, where some of you explained things, and maybe there was an error somewhere, so you only lost a bit of the marks. Those who went straight to the answer and got it wrong lost everything. And that is not the way it should be. It's up to you to do better. Okay, now, look at this. Look at the first column and the last column. They're the same, aren't they? That tells us something. That tells us that this equals x. That equals x. So just like in ordinary school algebra, there are some expressions that can be simplified. Complicated expressions can be simplified by using some basic facts, of which that's one of them. But you don't have to remember that, because once you remember the distributive law, which is just like sets and just like multiplication, you'll be fine. Okay. We say two expressions are equivalent or equal if they have the same Boolean function, like the one we just saw. So here's another example. That's that and that. Turns out when you write out the table, they've got the same, they're always the same, always the same. They represent the same function, always the same. The two columns are the same. That means that equals that, or that is equivalent to that, is what we sometimes say. Okay, so we can write that. Because the two columns are the same, because they're the same, we can write that. Let's have a close look at that. And let me go back to remind you of a couple of things. Let's go back to school for a moment. Say I've got A times B plus C. You can all expand that out, can't you? It's AB plus AC. Yeah, actually. What's O? Where did that go? Who said that? Oh, yeah, you're sitting next to me. You're sitting next to him, haven't you? It'll be unfair. All right. Well, that's oh no. Let's do sets while we're at it. Say I've got X intersect Y union Z. So now we're doing sets. Okay. Now you might not remember this, but go back to a few weeks. This is X intersect Y union X intersect Z. Now, let's go to this. This was A times B plus C, and we expanded that out, AB plus AC. Look at what we've got here, XY, or XZ. Same, isn't it? Or we can look at the sets. X intersection Y or Z is X intersect Y or X intersect Z. So it's X and Y, if I put the and in, or X and Z. There it is. It works the same. For sets, it works exactly the same.
So could we use this for proofs? Like this type of algebra for proof?
Yes. Yes, you can. Yes. Because what you've got here is rock solid. Firstly, do you really know that rule is true? Yes, you do. Because here is the table that proves it. This table proves that that equals that because we've looked at every possible input and they are always the same. Therefore, they're the same function. Therefore, they are equal. You now know that. Now that you know that, you can use it. Yes. Okay. So that's not too hard to remember. And there's the set example. There it is. It's like expanding. So that's not too hard to remember. So here's a whole table of stuff you might like to remember. Now that might look a little bit daunting, but it's not, really. There was a whole lot of things about sets I showed you some weeks ago. Does anyone remember a slide, something like this, with all sorts of set identities on it? Yeah, okay. Yeah, it's actually exactly the same, I think. But you can, when I write down the logic things, I can write down beside it each a set identity. The sets are a sort of Boolean algebra, really. So the logic and the sets work the same. The similarity with addition and multiplication is not exact. I used the idea of expanding A times B plus C as a way for you to remember things, but arithmetic is a bit different in some sense. For a start, you've got addition, subtraction, multiplication, division. You've got more operations and things are a bit different. But with sets, it's the same. So you can think of this if you've got Boolean expressions. If I say, I mean, you can check each of these out. Say I've got F or F is F. All can be proved with truth tables or common sense. I'm going to do this with a truth table. Say I've got 1, 0. F or F. Can you read that? I'm just doing a little truth table. If F is 1, then F or F is 1 or 1, but 1 or 1 is 1. That's just 1 or 1. If F is 0, then F or F is 0 or 0, and 0 or 0 is 0. So that says that F or F has the same value as just F itself. Now, if I'm thinking of this as true or false, if I'm saying something is true or true, it's true, isn't it? If I'm saying something is false or false, it's still false, isn't it? If I'm saying the answer is yes or yes, what's the answer?
Yes.
Yes. If I'm saying the answer is no or no, what's the answer? No. So that one's common sense. And the same with and. If I say something's true and it's true, what is it? Right. Okay, and so on. What about that one? Whatever this is, if I take that, let's do a little table. Where 1, 0, and then 0 is always 0. So if I take f or 0, 1 or 0 is 1, 0 or 0 is 0, and look, it's the same. F is the same as f or 0. They're the same. So each of these can be proved quite easily with a table. They're called truth tables because if we're thinking about true or false, then we call them truth tables, but they're just tables, like we've seen now about 5 or so already on the slides. And for common sense, if I say, well, the answer is whatever it is or false, then it's whatever it is. You might like to think about these to see if you can think if they make sense. This one, if I say something is true or false, it's the same as false or true, isn't it? Doesn't matter which way round I do it. This or that or this. Same thing? This and that is the same as that and this, isn't it? Right, so that's those two. Okay, they're exactly the same as a bunch of set identities, which means that all the stuff we did with sets means you've already done this, so I can assume you already know it, right? Yes, okay, good. Actually, all right. Now, by suppressing the and, some of the identities, as it says, are in a simpler form, and you might like to rewrite some of the ones on the previous slide like that. You may prefer to write them like that. I actually prefer to have them like that, but you might prefer to have them like that. Okay. Some more identities. Okay. These also can be proved by truth tables, but if something's not true, it's false. If something's not false, it's true. If some not, two nots cancel. Each of these, and we did one of these with our table, but these two are called De Morgan's laws. You can prove every one of these with a table. Every single one of them can be proved, not just proved with a table, but easily proved with a table. Okay. So far, nothing we've done is particularly hard. There's some symbols that are new to some of you, and a few words that are new to some of you, but what we're doing with them is not difficult. This, if you do a bit of work here, this topic will provide you with easy marks in the final exam. So it's worth a bit of work. You don't have to spend as much work as I know some of you did to get your head around proofs, or some of you did with some of the more difficult counting problems. This is an easier topic, but you must get used to notation and the words, and this is the basis for so much. Logical thinking, logical thought, proof, all sorts of arguments, as well as for those of you programming, it's necessary there. Okay. Now, the good news is you don't actually have to learn all of those identities because some of them are consequences of others. In fact, there's only about one or two that I find I really need to have any attempt to remember at all. And if I happen to forget them, I can check them with a table. So let's, just as an example, and it is as an example of how you can use these identities, we're going to prove that FF equals F. So that's short for F and F equals F. Now, this was in one of those lists of identities, but we actually could cross that identity off and not lose anything because we can prove it from other identities. Okay. There's some of the other identities written here from the previous slides. So let's start with f. From the one we've called 1 here, f is the same as f and 1. Now, by 2, 1 is the same as f or f dash, f or not def. So I could replace 1 with f or not f. So we've done it, f or not f. All right, things are becoming more complicated, but this is fun anyway. Now, this is like, we can expand this, just like the usual expansion. It's ff or ff dash. So there it is, ff or ff dash. Now, ff dash is 0 because that's true and false. That's that one there. If something's true and false, can't be, it's false. So that's ff or 0 because that has become 0. And ff or 0 is just ff because anything or 0 is just that anything. So we actually don't need all those identities. You can prove some from the others. And that's good practice, that. Good practice in thinking makes you look at the identities, use them, become a little more familiar with them. Okay, but as it says here, the enlarged list of identities is included because it's easier to work with. Also, a lot of them are common sense, and so they're just sort of somehow there in your head anyway once you've got a little bit of practice and done a little bit of thinking. Okay, so we did see by our tables a few slides ago that was equal to that. Well, we could have known that because xy or xy dash, we can see here, this is like a common factor, x. This is the sort of thing you can spot in algebra, so you'll be able to spot it here. We can take that out. It's x leaving in brackets y or y dash. Just like in algebra. That's one of the identities. But you sort of know it because you use it for algebra, something that's analogous in algebra. Now, y or y dash, that's like saying something is true or it's false. All right, yeah, that's okay. That's true. So that's one of the identities. That's that identity there. That gives us 1, and something and 1 is just that something. Okay, so we could have known that. But then you might find the tables easier to do it. So we've seen 2 proofs of that identity, one with the table, one using identities. Okay. Now, having tables is nice. If you've got a Boolean function, a Boolean expression, so if you've got a Boolean expression, you can do the table because you can just, with the expression for each input, calculate what goes there. So if you want a table, you can get a table. That's easy to do. But what about going back the other way? What if you've got a table and you want an expression, which you might want for something like, well, an obvious example, because some of you are programming, is that you might have a large table of things, and while you can enter a table into a program and have a table you can look up, that's fine. That's one way of entering information, having a program, writing a program. It would probably be neater to just say x or y, z dash. Sometimes you want that. Okay, so here is a method for starting with a table and ending up with a Boolean expression. Okay. Well, what we're going to say is this function is 1. We get 1. It's true. Or if you like, we get yes. If we've got this or we've got this. We get 1 when we've got this or this. That's a way of describing the function, isn't it? If I tell you, we get 1 when we've got this or this or this or this, and list all the cases in which the output is a 1. Okay. So we're going to look for where we've got the output 1. We get 1 when we've got x but not y, which is xy dash, or we've got not x or y. Not x, sorry. We've got to have 1, 0, which is 1 and 0. That is, we've got x and not y, and. or we've got this combination here, which is 0 and 1, which means we've not got x and we've got y. X dash and y, x dash and y. So if I tell you that this is when we get 1, the function gives you 1 when we've got that or that. Okay, so that means our function can be written like that. There it is. That's it. You've immediately got an expression. This is called the disjunctive normal form. What that means is the expression is this or this or this or this or this, because I'm looking at each of the ones and telling you these are the cases in which you get 1. And we can do this no matter how many variables we've got. I could have a table with 20 variables and we could do this. There's an example. That's our jacket function. Disjunctive normal form is going to be a bit of a pain here because there are 5 rows that give you 1. We get 1 when we've got x and y and z, x, y, z. Remember that's short for x and y and z. Or we could have x and y and not z, x and y and not z. Or x, not y, z, x, y dash z. And so because of the 5 ones, we get 5 terms here. That's a Boolean expression. It's not the nicest, but it is a Boolean expression for the function. It's the disjunctive normal form.
So the disjunctive normal form is the one before it's broken down? Like before you break it down?
Well, the disjunctive normal form is the one where we get, it's the one where we give all the possibilities separated by or. That's exactly the disjunctive normal form.
So if I break it down even more, do I call it a different name?
No, if you've got, it's like, we saw earlier that function was that,
Yeah.
then that's not the disjunctive normal form. Right. It's the disjunctive normal form is just when you list the possibilities for getting 1 and separate them by ors. We get 1 when we've got this or this or this or this or this. It's exactly when you're saying this row or this row or this row or this row or this row. Yeah. Okay. This tells us something. This tells us that this could be simplified to give that. And just as in algebra, when you've got a big complicated expression, you often want to simplify it, even if it's only because the examiner is going to give you more marks with that. But why use something complicated when you can do something simple? Okay. Here's one way of simplifying it. I'm not going to go through that. You can go through it yourself. It's using the identities step by step to go from the disjunctive normal form, which is something or something or something or something or something or something. There's been some brackets put around. That's just to focus your attention on those 2 terms, and then we'll deal with those 2 terms, and the various rules have been used here. I'll let you look at that. That's not the way we're going to deal with them. You can, and there is nothing wrong with it. We're going to use a visual technique called Carnot maps, which work with 2, 3, 4 variables. But I think it might be nice to take a break before I tell you about Carnot maps. Carnot maps are a lot of fun, but would you like a 10-minute break first? Would you like your tests back in your 10-minute break? Okay, tests back. Actually, see if I can... I'm going to read out your names. I'm going to turn this off. A lot of you did not write out explanation. You're like I used to be. Hate writing out things. You just scribble out the numbers and there's the answer. However, you do need to learn to communicate a bit more. You do need to write, explain. Especially for me, the marker, or whoever else is marking. It's not just that if there's no explanation and I don't know what you do and it's not right, you'll get 0. I mean, you do need to show what you're thinking, but you also need to develop the ability to communicate. And most of you are pretty bad at that when it comes to maths. And there's hope for you because I used to be really bad at that when it came to maths, and I have learned how to do it so you too can learn. But perhaps really importantly now, just for marks, explain a little about what you're doing. Because if you assume that I will know what you're thinking, you are wrong. If it's not on the paper, I'm assuming you're thinking nothing, okay? And I know you're not thinking nothing, for most questions anyway. So a little explanation, put in the steps. Don't cut corners, I see that too much with all sorts of things. People skip steps. You're much more prone to errors when you do that, and you should learn to communicate stuff. Okay, any questions about the test?
How does that, I don't know if you know, but do you know how that compares to last year's one?
No, I don't. I wasn't involved with discrete maths last year, so I don't know. I wasn't surprised. There was nothing about that that particularly surprised me. It's probably much the same. I know there's a lot of you who aren't here, so that's not the people I'm speaking to now. There are people who are doing nothing, and probably there's more of them in the bottom end, because if you work and do things, you should get some marks. If you feel that you're putting in work and not getting the marks you think you should have, come and talk to me, and we'll look at what's going on and what can be done to improve. Okay, so that's about it. How about we move on? I know I've taken your break with giving the tests back, but I thought you wanted your tests. For those of you who have friends who have not got their tests back, please tell them to come and see me and pick up their tests, like a lot of people had before anyway. If you want to come and show me your test and argue for more marks, go for it. You probably won't get any, but we'll have a fun chat on the way anyway. All right, let's continue. For the second half of this lecture, I am going to show you about Carnot maps. Okay. Carnot is spelt like that. It's, where is it? We're off the bottom of the page, so I need to zoom back so we can read the whole slide. Carnot. Okay, I'm going to show you this lovely pictorial way of simplifying expressions that saves you all that work. Now, for me, I think there's few things in life you can do that are more fun than something like that, but some of you might like to do it another way. So here we go. So we've got a function, that's our jacket function, our example we've looked at quite a few times. We know a simple expression for it. We just looked at it on the previous slide. But let's see if we can find it easily. Now what we're going to do is start with a rectangular table. There's a couple of things here you've got to be careful about, really careful about, or you will completely and totally stuff it up. But if you get it right, it's easy. We've got three letters, X, Y, and Z. Now, there's quite a few choices. There's probably 12 different ways of doing this. But they're all really the same. They're all really the same. We've got three variables. We'll put one down here and two across here. So the x's, I'm going to put x and x dash. I'm going to cover every possibility, basically. And across the top, I'm putting every possibility of y and z with knots in there. YZ, Y not Z. Not Y, not Z. Not Y, Z. See, we've got all four possibilities we can have with the knots and the Y's and the Z's across here. Okay. Now, the important thing here is that as I move from one to the next, only one of these changes. Y remains Y, Z changes to not Z. Going from here to here, Y changes to not Y, but Z dash remains Z dash. It's really important that it's critical that as you go from one to the next, only one changes. Here, y dash stays and z dash changes to z. And we're actually thinking of this as wrapped around. So as I go from here to here, y dash changes to y and z remains as z. So we're actually thinking of this as wrapping around. And down here we've got x and x dash. The idea is that each box represents one row of the table. We have 8 rows in the table. We have 8 boxes. Have you got a question?
I was just wondering in relation to like the columns themselves, so y, z, y, and then the next one is y, z dash, and y dash, and z dash, and y dash, z dash. Does it particularly matter like if you switch it around, will that affect the map itself?
No, you can choose, let's choose another way that we could do it. We'll choose a couple of right ones and a couple of wrong ones so that everybody can see, because I think it's a good, very good question. Actually, that question deserves an egg, doesn't it? Yeah, I like good questions. I like good questions. Give you an egg. Who else looks like you need an egg? I didn't give you an egg. It's a different. All right, you want an egg? Yeah, I don't have an egg. All right. I've got some more eggs. I'm not going to leave here with any of these eggs left. So, okay. All right, let's say you didn't want to start with YZ. Let's say you wanted to start with YZ dash. Okay. You can start with whatever you want. I've got a choice of what I can put next. Would somebody like to give me something I can put next? Y dash Z dash. This is okay because Z dash stayed the same and I changed only one thing. Okay, now, would I put YZ dash here? I wouldn't. It's changed one thing. I've changed the Y but not the Z dash. Why wouldn't I put it there then? I've already got it. Okay, so I'm not going to put that there. What am I going to put here then? Y dash. And just Z. That's okay because that stayed the same and I changed the Z.
I was just going to say you'd probably want a little bit of a system where you might start confusing the sound effects.
Yeah, all right, system is, all right, let's change Y here. For the next one, we'll change Z. For the next one, we'll change Y. For the next one, we'll change, that's actually one way of thinking of the system. But if you check that you've got all 4, and that as each time you go from one to the next, you change one letter, you'll be okay. What will I put here? YZ. And that's correct because I've changed the Y but not the Z. And then if I was to wrap around, I'd be changing the Z and not the Y. So, Adil, does that answer your question? It does? Good, okay. Does that make it clear to everyone else?
Do you always go from right to left when you add the dashes? So, for instance, if you have
Let's do another one.
So yeah, if you had YZ, could you just go Y dash Z, or is it just...
No, I could go Y dash Z, that'd be fine. That'd be fine. So what would I put next if I decided to...
Y dash Z dash.
Y dash Z dash. And what would I put next if I decided to keep going?
Y Z dash.
Is that right, everybody? Yep, okay. So that's correct because I've got all 4 possibilities here and from there to there I changed the Y, from there to there I changed the Z, from there to there I changed the Y. It's all right. As is that one because I've got all 4 and yeah, okay. So there's lots of different ways. It looks like there's lots of different ways, but as we sort of really consider the table as wrapping around, it's fewer ways, and it doesn't matter whether you go forwards or backwards. So in one sense, there's only one way, but there's a lot of ways of actually representing it.
I just want to confirm, so let's say that top one.
Yep.
YZ, Y dash, Z. Could you go then Y, Z dash? Could you go like that?
Okay, if I went Y, Z dash, then I'd be changing the Y and I'd be changing the Z.
Is it still valid?
No. No. So that's, I've got to change only one thing each time.
Oh, change one thing.
Change just one thing. So that's a really good point. I would not put YZ dash. So thank you for that. We must change one thing. If we changed both and went there, it would completely stuff up things. It would completely stuff up things. Okay. So I have in this table 8 boxes. Each represents one row of our table in here. But which represents which? Well, this, we've got X, yes, true, Y true, Z true. We've got X, Y, Z. So X, Y, Z, that represents this box here, X, Y, Z, because they're all ones. We've got X, we've got Y, we've got Z. Yes, 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 true, true, true. So that row, that corresponds to our X, Y, Z, so that one goes there. Now, this is, yes, we've got Y, Z, we've got, sorry, X and Y, X true, Y true, but not Z. 110, that's X, Y, but we haven't got Z. So it's X, Y, Z dash. There's a box for X, Y, Z dash. That's this one here. See, it's X, Y, Z dash. So that one went there. Now, this one, let's have another colour. What about this one here? We've got X, not Y, Z. X, Y dash Z, because it's X, not Y, Z. X, Y dash Z, that's that one there, isn't it? Isn't it? Okay, so that one went there. So each of these ones gets put in its right box. X, Y dash Z dash, X, Y dash Z dash, so that goes there. And then we've got, almost out of different colours. X dash, Y, Z, X dash, Y, Z, that's there. So that's there. And so on. X dash, Y, Z dash, X dash, Y, Z dash, X dash, Y, Z dash, and so on. Can you see how you place the numbers from our table into the boxes? I think do we have another example? We can do another one later if we want another example. Okay, that's the Carnot map. We've mapped these into here. Now we've done this so we can do something visual, because we can see a relation. We now look at where we've got ones. We can look at where we've got ones. We're looking for blocks of ones, and we look for the largest blocks of ones we can get. Now we've got the largest block of ones we can get, and we're looking for blocks of sizes which have powers for 2. So our blocks are going to be, all right, we're not going to get a block of 32 or 16 here. With something like this, we could get a 2 by 4 block of ones if they were all ones. Or we could get a 1 by 4 block, or we could get a 2 by 2 block. That'd be a way of getting, if there's a group of 4 ones together, they could be a 1 by 4 or a 2 by 2. And then we could maybe get some blocks of 2. So we could get, a 1 by 2 or a 2 by 1 block. And then we might have some things all by their little lonesomes. So we're looking for big blocks. I can't get a block of size 8 ones, but there is this block of size 4 ones. Okay, we circle that. What that tells us, let's think about what it tells us, that that's a whole row here. It's ones. It says X. It says the function is 1 whenever we've got X. Doesn't matter if we've got X is 1, if we've got X, it doesn't matter what Y and Z are, the function value is always 1. So that simplifies the description of it. Okay, that covers most of our ones, but we've got to make sure we cover all the ones. This one hasn't been covered. Now, I can't cover this with a block of size 4. I don't want to cover it with a block of size 1 because I can cover it by a block of size 2. And a block of size 2 is easier to describe than a block of size 1. Now, what does this say? This says that the function value is 1 whenever I've got yz. As long as y and z are both true, or y and z are both 1, doesn't matter what x is, the function value is 1. So I can now, using those two blocks, describe the function. We get 1 for the function when we've got just x, when x is 1, or when yz is 1. We don't need to give the complicated disjunctive normal form, which had 5 different terms. Function is 1 when x is 1, or when, I'll do this in purple, yz is 1. So that describes the function, doesn't it? The function is 1 when we've got x or yz. Agree? And we saw that by picture. It's an easy way of doing it. It's not, I reckon it's not as much fun as doing it this way, but it's easier. And you might think it's more fun doing it pictorially anyway. Okay.
With that, because before you might talk about it, but like you were saying, you've got like 4 variables. Can you go more than 4 variables with a Kano map?
If you're really good at thinking in 3 dimensions with things like this, yes, you could.
Okay, so it becomes 3 dimensions. You can't just keep adding like.
No. No, not to get all the relationships you might want. I don't know whether people use Kano maps in 3 dimensions. We can do this with 4 dimensions because I'll just do the same thing down here. As 4 things across here, I'll do 4 things down here. You won't be given anything with more than 4 variables. But you could make it 3-dimensional.
Or you can just make it longer, right?
You'll miss some of the relationships if you do that. You'll lose information about what's close to what.
So if you were doing way bigger things, you probably wouldn't want to do it for 3 anyway. You'd probably want to write a program that did it for you or something.
Yeah, I'd look at other ways of doing it. I'd also look for sub-expressions, which were only 2 or 3 variables, and just simplify those with Kano expressions. You'd have to really think about it and use all the techniques you did.
The Kano map, once you get more than 4, isn't really the best thing to use.
No, it's not nearly as easy. No, it's not. No.
If you put Z on the left-hand side, you're going to have like spotty ones and zeros. So you have Z on the left-hand side, you have X.
Oh, if I put the Z there instead of...
Yeah, you're going to have like spotty ones and zeros.
It will work. Let's do it, just for fun. Let's do it. No, I think it's a good exercise because we need some practice in these. Where's our original function here? Let's, no, that's the next one. Let's go. All right, there's our function. I'm going to do another table. I'm going to do that because I think that's a really good idea. I'm going to squeeze that in here. So we're going to put Z there and Z dash. And then across the top, you happy with if I start with XY? What do you want next? XY dash. What do we have next? X dash Y dash. And finally we have X dash Y. So does that say X dash Y or XY? Let's make sure it actually looks like XY dash, otherwise it'll look like some of your tests where I couldn't read anything. Okay, I'm not being insulting about anyone's writing in particular, but some of it was pretty bad. Okay, let's fill this in. XYZ, there's a 1 if we've got XYZ, that's a 1 there. We've got a 1 if we've got XYZ dash, XYZ dash. We've got a 1, XY dash Z, XY dash Z, XY dash Z. I've got a green one if I've got X, Y dash Z dash, X, Y dash Z dash. got a 1 for x dash, sorry, x dash yz, x dash y z, x dash yz. Okay, and the other are where the zeros go. That's our x dash yz dash, x dash yz dash, just 0, and then we've got those 2 zeros. Okay. Well, I do have, now this was a good example. This was a really nice question. This is do you like Easter eggs? Oh, that's right. All right. Who would like, you haven't had an egg yet, have you? That was an egg. All right, that was an egg-worthy question. See, I like people who sit up the front. That's why people who sit up the front get more eggs. I mean, it's not that I don't like you guys up the back. It's actually that I'm a lousy shot with Easter eggs. That's the problem. I'm a really bad shot with Easter eggs, or anything else I might throw at you. Now, this is, well, I can see a 2 by 2 block here. Can you see a 2 by 2 block of ones? You can see a big blocks first. Big blocks first. Let's do this one first. Now, very, very good point there. Because we think of this wrapping around, we've got a block of 3s here, haven't we? That one wraps around to those 2. But I'm not looking for blocks of 3. We're only looking for blocks of size 2, 4, 6, 8. That is blocks that are 2 by 4, 1 by 4, 2 by 2, 1 by 2, 2 by 1, things like that. It's just powers of 2s. So I'm going to ignore, I'm not going to take a block of 3. However, I do have a block of 2 here. I'm not going to take this one all on its lonesome. I'm going to wrap, that wraps around, so I'm going to take a block with just those 2. Okay. So this looks different to what we did with this one. This one looks different to that one, doesn't it? But in essence, it's the same. We've got a block of 4 and a block of 2 here. Over here, we've got a block of 4 and a block of 2. And that's important. No matter if you do this in a test and you all do it correctly, say you were doing this one, you'd have your boxes looking different and your labels looking different, but you could all still all be correct, and you'll all end up with a box of 4, a group of 4 and a group of 2. Well, we've got ands and ors. This is x and y and z, which is x, y, z is x and y and z. Or what we're doing is we're saying don't swap your ands and ors with this. That's probably the best thing. Don't swap it. What we're saying is we can get 1 if we have those x and y and z, or we have x and y, or we have x and z, or we have. That's what I'm saying. So don't swap your ands and ors with this.
I wasn't thinking about that slide stuff.
So really this map is saying we're looking at every instance of and. For example, x
yes,
and
yes,
y
yes, yes.
Not x and y and not z.
That's right. Each box is an and, x dash and y, z. And y and z, x dash and y and z dash. Yes, each box is an and. Each box is a row. Each box is this. And this says x and y and z. This says x and y and z dash. This says.
So we derive the or stuff later.
Well, we're saying the or comes in when we say we get a 1 if we've got this or this or this or this or this.
Right.
That's how the function we get 1s. Or if you want to think in terms of circuits, that's how we get the current to flow. Okay, let's just look at what this tells us, because hopefully it'll tell us what the one over the page does. If not, something funny is going on, or maybe something interesting is going on. This block here, clearly Z or Z dash, doesn't matter what Z is for this block here, does it? Doesn't matter what Y is here, Y or Y dash. What's common to this block is that this block can be described as X. Doesn't matter what Y is, doesn't matter what Z is, you've got to have X. Do you agree with that? That's what describes this block? x. You see, we're looking for blocks which will give us information of this sort, and that's why we've got to have only 2, 1 or 2 or 4 wide, or 1 or 2 or 4 deep. Now, what is it about these two here which we've grouped? We've got z. They both have y. Doesn't matter what x is, but yz. These two are yz. So the function value gives us 1 if we've got x. Doesn't matter what yz are. Or if we've got y and z, which is what's common to those two things. X or yz. X or yz, that's what we got over the page. It's fun, isn't it? You can have so much fun with this. Okay, now you will need a little bit of practice with this because some people forget that you can wrap around, and sometimes people will just take a single block instead of 2. Now, if you take a single block, gee, should I show you what happened if I'd taken a single block and not combined those two? Yeah, I should. Okay, what if I've said, I've covered those ones, now I'll just put a single thing here to cover that. I'd have said, all right, I've got x there, doesn't matter what the y's and z's are, and the function is 1 when I'm in there, or the function is 1 for this, which is x dash yz. Now, that's correct. It's correct. If I leave out the x dash, that just says, or I've got yz. Doesn't matter whether it's x or x dash. This leaves out the case that we've got x along with y and z, but that's captured here. So these are both correct. It's just that this is simpler. And that's why we use bigger boxes rather than when we can get away with it, because a bigger box has a simpler description than a smaller one. Question? I'd probably take off half a mark. I want you to be perfect. The Carnot map method is the one that gets you it in simplest terms. That's the Carnot map. So if we go back to the steps, if it says use Carnot maps, that means using the biggest possible blocks. That's part of the method of Carnot maps, is to use the biggest blocks, and so not to do that. So I'll cross that out.
Is there a name for the simplest form? Because for the other one it was called non-disjunctive.
Disjunctive normal form.
Yeah. Is there a name for the simplest one?
Not that I'm aware of. I'd call it simplest. But there isn't a unique simplest, because sometimes you could have two different things that are just as simple but different, I think. Yes. But there is one disjunctive normal form.
Yeah, so the question might ask, do a disjunctive normal form, is that correct?
Yes. A question might say, find the disjunctive normal form, and you'll be given something as a table.
If we put the simplest one, we'll get it wrong.
That's right, because I've asked for this disjunctive normal form. But then there might be another part which says use Carnot maps to find a simpler expression, in which case I'd expect you to, using the biggest blocks possible, which means I'd expect this answer. And if you gave me that answer, you would clearly have got most of it right. Firstly, logically, this is a correct expression, so it's not the end of the world. It's just not the simplest. It's just the sort of, it's not exactly the method, and it's a bit like taking half a mark off you because you didn't simplify your algebra for the answer for a question. It'd be that sort of thing. But the Carnot maps mean you take the biggest blocks, which means you'd get that one rather than that one. But logically, that's not wrong. Logically, it's not wrong. Okay. I like Carnot maps. It's like just playing games with Okay, now that's all right. That slide's just a summary of what we've talked about. There it is. So you've got it at home. Now let's do another one. This is much the same as the previous one. You should do a few examples. You should do a few examples of these. Just so you get used to the sort of things to look for. The wrapping around, which people forget, and also some people stuff up these and go straight from YZ to Y dash Z dash, change two things instead of one. Yeah, there's a few things to practice, and once you get over the simple mistakes, there's nothing tricky or difficult. Okay, this is like the previous function, except we've got an extra 1 there. So only one thing has changed from the previous example, and that's a 1 there, which gives us a 1 in that box there. So see, the previous example had that Carnot map, the one below. Oops. Oh, bugger. I've ruined the fun. The previous one had that one, and now we've got a 1 there. Damn. Oh, well. All right. I've blown it. Anyway, all right. So you can see some blocks here. All right. Tell me, where's the block?
The top.
The top. Right. So that's a 1x4 block. Yes. Now, we're not finished because we haven't covered all the ones. So, how can I cover the rest of them?
Because of that, so you get like the 4, but since it wraps around, you can get 4 of them.
Yeah. It's like this, isn't it? That's where, you see, this is, so you imagine that wraps around. Can you imagine that? And then those two are next to each other, so you've got a block of 4. Now, if you took that block of 2 and that block of 2, you would get a simpler expression, but going back to your question, it wouldn't be the simplest and it wouldn't get you quite full marks because we want the simplest. I mean, sometimes you really do want the simplest thing. For example, if you're doing lots of calculations with algebra, you want the simplest form of your equation, not the longest. And even if you're using a computer to do your calculations, sometimes you do need simple things because computers can't do everything. The only programming I've done in about the last 20 years has been pushing the bounds of either space or time, and the most important thing, apart from correctness, has been efficiency, where the stuff doesn't work at all if you're not careful. You've got to be as careful as possible to get as far as you can because you run out of time or you run out of memory. And even though we've got large computers today, I can give you hundreds of problems where you run out of space or you run out of time. Okay. So this will give you something simple. We know what the red box will give us. What does the red box say to us? The function gives you, your expression gives you 1s, your function gives you 1s when you've got x. Now, what does the purple box say? So you've got 1s when you've got x, or, sorry?
You don't need y because there's y and not y.
Right.
And it's also x and not x.
So that's the common theme of this, isn't it? You've got z. Doesn't matter what x is, doesn't matter what x is. And when you look at these two, doesn't matter what y is. That's right, it's x or z. X or z. And that's probably what's on here. Oh, look, we got it right, x or z. Yay! Okay, so that's all written here. All right, you can do this with 4 variables. And why did James fill that in? It would have been so much fun doing it ourselves. Never mind. So we've got variables x, y, z, w. Same across the top. Down here, we can put our w's here, but it's the same idea. You can start with whatever you want, and as you move down, you change one thing. We've changed x to x dash to go from here to here. To go to the next one, we changed w to w dash. To go to the next one, we changed x dash to x. And it wraps around. To go from here to here, we change w dash to w. So we imagine this wraps around. It wraps around both ways. Okay, so can you see the labelling? Good. Now we look for blocks. So the biggest block we could possibly get is a 4x4. That's if it was all 1s. But we haven't got that. So we now look for blocks of size 8. So a block of size 8, we can't get 8 by 1, but we could get a 2x4, 4x2, and that's where we see here in red, this here, it wraps around, it gives us a block, a 4x2 block, so that's done that. And then we've still got these two ones not covered. So then we'd look for blocks with 4 things in them, so it might be a 1x4, a 4x1, a 2x2, but there's no blocks of that form that could cover these two ones. Because if I wanted to try a 1x4 block, I'd have that one, that one, that one, and that one, but that's not a 1. So the best we can do is go to blocks of size 2, and that gives us the green block and the blue block. And once we put them in, we've covered all ones. So we can say the function is 1 if. I'm going to cover that up with Easter eggs. Right. Now, what does the red block tell us? What's the common feature of every expression here, wx, yz, wx dash yz? What's...
Similar to the last question, Z.
It is. That's the way to describe that block, isn't it? This block is exactly it consists of all the boxes where we have Z. Doesn't matter what X is or Y or W, these are exactly the boxes with Z. So the red one gives us Z. Or. Now what about the blue box? What describes those two ones in the blue box? WX, yeah, clearly they've both got WX. Y dash, yeah, because these are exactly the boxes which have WX, Y dash. Doesn't matter what Z is. Or the green one. Can you read that? W dash, X dash, and what was that? Y dash. You probably don't need to read that because that's probably what's under the eggs. It is. Yes. Yes.
I actually have a question in relation to the variables. So let's say in the row section you have one variable, and then in the column section you have 3 variables. So let's say for the rows it's like W and then W dash, and then on your column section you have X, Y, Z, X, Y, Z dash. Could you have it like that as well?
All right, so I say I started down XYZ dash. All right, and then I could put down, I don't know, X, Y dash, Z dash, and I could keep going. And I could list 8 things down there. There are 8 possibilities with X, Y, and Z. But what I'm losing if I do that is that, let me do an X, let's change X dash, Y dash, Z dash. I'll change a Y, X dash, Y, Z dash. Then have I got what I want? Yep. The really important thing here is that when 2 things are next to each other, it means they differ by exactly 1 variable, the value of 1 variable. So let's say these 2 here, the W value is the same. We've got W, we haven't got X, we haven't got Z. They only differ in Y. They differ with 1 thing, and that's really important in getting this information. So if I list 3 things down here, then if I look at these 2, they won't be next to each other. The boxes representing these 2 won't be next to each other, but they differ by 1 thing. It's only the X that differs here. And that will mean that I won't get the simplest possible expression. I might miss things. I don't think I've convinced you.
No, I get it. But I'm just thinking of like instances when it's more than 4 variables, such as 5
Right.
variables. Like,
Yep. Okay. If you did that and took it down, you might see something and get a simpler expression, but you might not get it as far as possible. Yep. So as long as you label and read off carefully, you won't do anything wrong. So yes, it might give you a simpler expression. I mean, it would if you can see something. If the diagram then shows you something, you can pull something out and get something simpler. Yes, but it might not be the simplest. That's why if I had a fifth variable, I'd rather think of going up and building my table up with say my next variable was u. I'd have u and u dash. I'd have 2 layers. And then I'd have to think about layers. So I'd have a 3-dimensional array.
So it'd be the same table, just one with u dash?
Yes, that's right. Yep, u dash, yes.
also, you're considering if there was a big variable, it would start to go into like a cube.
Yes.
So, that's when it starts to get a bit convoluted.
Yes. And if you get quite a few more variables, you could always go to 4 dimensions.
So are we just switching dimensions into like I mean, switching things we're getting too complex or too lengthy into dimensions?
Well, but what we're doing is we're looking at a pictorial representation which is useful for telling us when we can simplify expressions. That's basically all this does. And if you want to continue this sort of picture to capture all the information, after 4 variables, you have to go up a dimension and then add a few more variables, and to capture all the information, you'd have to go up another dimension.
I can turn this into a 3D array as well, right?
Yes, you can. 3D, yes. Yeah, but when it gets to 4 dimension, it gets harder to visualize. Not impossible to work with, but harder. Yeah. So you can have all sorts of fun. Now, I'll bet you anything James is not going to give you a question that's going to for which you're going to have to use 3 dimensions. I might ask him to put in one for which you'd have to use 4 dimensions. He'll think it's a great idea, but I promise you he won't do it. Yes?
Can we tear apart our test sheet and make a torus to do this so that we make sure we don't make any errors?
I don't think the exam instructions say you are not allowed to tear out a page. You might upset the supervisors and entertain everybody, so could you leave it for the last 5 minutes of the exam if you do that? Because you might upset a few people. But yes, ideally, you'd tear it out, you'd wrap it around this way, and then you'll wrap it around that way, and for that you need stretchy exam paper, and you'll make yourself a donut or a torus. Yeah, there's all sorts of stuff you can do. You see, you can have a lot of fun with this. Now we're getting into the mathematical area called topology. I think we've strayed a little bit from where we were supposed to go, but there's a lot of fun to be had. Okay, now, we probably should go back and look at the last slide. We're on to the last slide. Oh. Okay. It says, use Carnot maps to find a simple Boolean expression for the following Boolean function. Now, that's one function. Because we've got 4 variables, we need 2 times 2 times 2 times 2, which is 16 rows. So James has spread it over, broken it up into 2 pieces. It's actually one table with 16 rows that he's set out like this. Okay. Does he put the answer on the back? Oh, no, okay. So Carnot maps to simplify that. And I'm not going to do that now. I think you should do it. Do you think you should do it?
Yeah.
I think you should do it. If you want to, if you do it and you want to know if you're correct, you can email me. If you do it and you want me to present the answer in the next lecture, email me and I'm happy to do it and to just show the picture and the final answer at the next lecture. But I don't want to do that now. Firstly, because I don't think I've done it. And secondly, because I don't want to deprive you of the fun, or more importantly, the learning opportunity that doing a large one like this will do. It'll be good for you. And if this one gets a bit hard, take a couple of simpler ones from the cheat sheet first, email me, whatever. And over here, how would you do that? This is another one I'll leave the fun to you. This is not too hard. I'll just tell you how you'll start this one because you know how to do it, but why not? Why don't I just start it for you? We've only got 3 variables here, x, y, z, and then we've got a function, let's call it f. Okay, so this poor electrical engineer has a circuit like that and wants to simplify it because maybe the person who soldered it is crap at soldering and you're much more likely to get a good circuit if you have fewer joints. That's always a good thing. Okay, so you've got all the possibilities. I don't have to put them in the same order as they were done before. I don't even know if this is the same order. Anyway, you're gonna have 8 rows, right? Okay. Oh dear. All right, let's say that all switches are on. All switches are on. Oh, look, current will flow, won't it? Clearly. Okay. What if X and Y are on and Z isn't? X and Y, no, that's off. Okay, no. Can we get current flowing through this way? If X is on and Y is on, nope, we're stopped. Okay, if X is on and Z is off, oh, it looks like that's a 0. Is that right? Okay. Okay, so you get your table, you complete that, and then you do your Carnot map. And I think this one works out nicely. I don't know. If you want me to present the answer in the next lecture, email me and ask me. If you want me to show you working and ask me if it's right, email me and show me. But I'm not going to tell you now, okay? I think we're out of time. Okay, who wants an Easter egg? Okay, let's get all my eggs because I do not want to take an Easter egg with me. So who wants an Easter egg? You haven't given you an Easter egg. Who else wants an Easter egg who hasn't had one yet? And then I'll give out ones. Who else wants an Easter egg? Adele, are you having an egg?
No.
You're being good, aren't you? Oh, sorry.
I passed
the exam, can I have a chocolate?
Yeah, that's good. Well done. Well done. 2 over here. Come and get yourselves. Oh, if you pass the eggs across to them, that'd be great. He's going to pass you eggs. Good. Anyone over here want an egg? Yes, you all want it. All 3 of you want an egg? Here, 3. Okay. Any of you guys over there want an egg? You're such healthy people. Want an egg? See, people up the back do occasionally get eggs. Who wants? You'll have the last egg. Okay. All right. Thank you, everybody. Please practice the Carnot map stuff because once you've done a few, it's easy. If you don't do any, you'll lose your marks. You'll end up stuffing it up and get 0. You do a few, it's easy marks. Okay, I think it's the break next week.
Yes.
Good, okay, see you in a couple of weeks. Tell your absent friends that they're to come and get their tests from me. I don't want to feed these tests to the cockroaches in my office. I'd rather they be collected by their rightful owners.
I was like, he's not serious. I looked at him, I was like, shit. Thank you.
Good, thank you. Right, hold on.
I'll go. Yeah, I think
Don't worry.
yeah. You don't do it. You don't do it.
I need to teach you something. Okay, so who's got first question? Right, okay.
Bro, you got 20 on my team. You got 20 in shot. I got 20 on
Yeah, I mean, you just like, you just Like this is
I would like to see the example. Yeah, like I should have done these like I think that's pretty much. Yeah. Well, I mean,
Yeah, I know. It's just like some of the things are putting blood.
Yeah. Anyway, it is on time. So you got
So you got halfway there. That's good. That's good.
Hey, there's my question.
This one and a half.
Does this work?
I thought I was going to get 35
Oh,
What's this one?
I should just throw it. I got one. But I can't
and
do
the
it.
next thing is when we're talking about the size of the sets.
Yeah, I got the last one. Yeah, I got the last one.
That you didn't use it's the whole thing about everything is great because there were 4 months. Try and yes.
So even if it doesn't say how to show for the working on time too, right?
Yeah, I didn't get that one right either.
Yeah, everyone, we did the same thing.
Solutions not active.
I just love doing like
Yes.
Yeah,
Yeah, because like
they're like in touch when blue in the face.
exactly
Nobody
like
listens
the
to you.
light here.
I don't know how.
But anyway, maybe you just
Yeah,
next time.
And every now and then I just check out on these Bible beach things to see if the weird thing works. And I love it.
Yes,
Rather than
yes.
set that one.
Oh yeah,
Yes, that's right.
There's multiple ways you can do it, but that's not the only way.
Like
There's another
something
one. There's another way you can do it.
shit works.
yeah, there are other ways.
Sorry.
I swear, it's normal right there.
This is amazing, bro. Congratulations. I think you're like at the top mark. You're not
Imagination, but not.
I just have.
Yeah, he's got like 33.
Yeah.
I would say time, but my brain is still static, my head, and sometimes after.
Yeah. It's tough because like you're anxious and also the way you want to cover all avenues to make your end.
Like this on tutorial, technology things, and you have to get this one. And it doesn't mean you don't
Maybe this side,
just means
I
you don't
don't
know
know.
melody.
And it's like tough stuff, you know, falling
Logged on.
Yeah.
I did.
I don't know whether I'm still logged on here. This has probably thrown me off.
Yeah.